who designs a microcontroller based on ARM Cortex-MX processor. So the on-chip communication, that is the communication between a processor and the peripherals and the memories, will be governed by a bus interface which is based on this specification, that is AMBA. AMBA specification supports several bus protocols. There are two important bus protocols called as AHB and APB. These bus protocols are derived from the AMBA specification of ARM. AHB Lite stands for AMBA High Performance Bus and APB stands for AMBA Peripheral Bus. Let's understand more about AHB and APB. AHB Lite bus is mainly used for the main bus interfaces on the microcontroller. APB bus is used for a private peripheral access and for some on-chip peripheral access using a bridge called AHB to APB bridge. AHB Lite bus majorly used for high-speed communication with peripherals that demand high-speed operation. APB bus is used for low-speed communication compared to AHB, and most of the peripherals which don't require high operation speed are connected to this bus. Let's say how ARM Cortex-MX processor communicates with the external peripherals. Now the peripherals could be memory such as code memory and data memory, and it could be a communication related peripherals or any other peripheral. Processor gives out 4 bus interfaces. These are all AHB bus interfaces. By using these bus interfaces, you can connect different kinds of memories or peripherals. If you check this part here, the processor gives out 2 AHB interfaces to access the code region. First interface is called as I-code, and this is decode. On the I-code bus, the processor fetches the instructions and vector table from the code memory. And from the decode bus, which is also based on AHB bus protocol, it is going to access data from the code region. What kind of data you store in code region, like constant data or any tables, something like that? That means processor uses 2 dedicated bus interfaces to fetch instruction and data simultaneously from the code region. That means whenever you execute an instruction from the flash, let's say, that's a code memory in our case, flash memory. Let's say if this is flash, then instructions and vector table will be fetched over this bus. And if you want to do any data access to the flash, then that will be carried out on the decode bus. After that, the processor also gives one more AHB bus interface. That is for the system bus. It connects to the various on-chip peripherals of the microcontroller, and through this bus, the processor also communicates with the SRAM. That's a data memory. Any data memory access, that is RAM access, is carried out over this bus. And also access to the various peripherals of the microcontroller such as ADC, DAC, timers, CAN. All these are peripherals of the microcontroller. Those communication will be carried out over this system bus, which is also an AHB bus of 32-bit wide. After that, the processor also gives out one more AHB interface called as PPB, that is Private Peripheral Bus, and through this bus, processor communicates with the private peripheral bus region. The private peripheral bus region includes most of the peripheral registers of the ARM Cortex-MX processor, such as NVIC registers, SysTick timer registers, and system control block registers. All control and configuration registers of ARM Cortex-MX processor will be part of this private peripheral bus region. That's how the ARM Cortex-MX processor communicates with memories and peripherals of the microcontroller. Let's take one practical example. Take a look into the block diagram of STM32F407 microcontroller to see how exactly the processor communicates with its various peripherals. For this, you have to refer to the data sheet of your microcontroller. Let's refer to the data sheet of STM32F407BG. Here I have a data sheet of STM32F407X microcontroller. Let me go to this section, device all, and here it is. This is a real block diagram of this microcontroller. Here you can see that there is a processor. The processor is based on ARM Cortex-M4, and it also has FPU unit, that is floating point unit. You can see that these are all the peripherals of the processor, like MPU, ETM, NVIC, the debug unit, FPU. So all these are peripherals of the processor. These are processor specific. Now to access these peripherals, it will be using PPB bus. These fall under private peripheral bus region. You can see that there is a flash. This is our code memory. This is embedded flash. This is on the microcontroller. So this is given by the microcontroller vendor. The processor communicates to this flash over D-bus and I-bus, or D code and I code. I stands for instruction, D stands for data. There is another bus interface which is given by the processor called S-bus. That stands for system bus. All D-bus, I-bus, and system bus are connected to a bus matrix. Now the bus matrix is given by the microcontroller vendor to synchronize multiple bus access from different bus masters. Here we have a couple of bus masters. One is the processor itself is the bus master, and after that we have Ethernet, which can also act as a bus master. USB also can act as a bus master, and DMAs, they can also act as a bus masters. When you have multiple bus masters, so a proper access to the bus should be taken care by another engine called arbiter, that is also called as bus arbiter. All these are part of the AHP bus matrix engine. If you just analyze this diagram, you can see that this is a main bus, which actually connects to the system bus of the processor over this bus matrix. This is a main bus of the microcontroller that is based on AHP protocol. This is the AHP bus. There are multiple AHP bus on the microcontroller. For example, this is AHP 1 bus. And we also have AHP 2 bus here, which actually connects to the camera interface and USB OTG peripherals. Those peripherals require a high operation speed. AHP 2 also connects to the system bus through this bus matrix. And AHP 1 also connects to the system bus through this bus matrix. That's why there must be one arbiter in between to handle the traffic which comes over different bus interfaces. That's the job of AHP bus matrix. And you can see that there is also AHP 3 bus. The AHP 1 is a main bus here, and so most of the peripherals are hanging on that bus. For example, all these I/O ports are hanging on AHP 1 bus. That means the GPIO port A communicates to the processor over this AHP 1 bus. After that, you can see that this main bus connects to the bridge here. This is a bridge which converts AHP signals into APB signals. Because there are some peripherals which don't require high operation speed are connected to APB bus. APB is also a bus which is kind of low performance bus compared to the AHP bus. The peripherals which don't require high operation speed are connected to the APB buses. This design also helps microcontroller vendor to reduce the power consumption. Instead of populating all the peripherals onto the AHB bus, so they implement multiple low performance bus interfaces, and they connect the peripherals which don't require high operation speed to APB bus. Now you can see that there are two APB bus on the microcontroller, APB1, this is APB1, and this is APB2. The APB2 can handle the speed up to 84 megahertz, and APB1 can handle speed up to 42 megahertz. Most of the communication related peripherals such as UART, SPI, I2C, CAN are all connected to the APB1 bus. Whenever, let's say you want to connect to a sensor which is based on I2C, let's say, you connect here, isn't it? You connect to the pins of the I2C, and that traffic is carried over APB1 bus. After that, it goes to the bridge, and after that, the APB protocol is converted into AHB protocol, and then it comes over this main bus, that is AHB. Then it connects to the processor over the system bus. That's a data path. I would suggest you to explore this diagram for your microcontroller. Just open up your data sheet, and if you are using ST microcontroller, then I think you would definitely get this diagram. That's about bus interfaces of the microcontroller. To summarize, this ARM Cortex-M4 processor gives out majorly 4 bus interfaces. All are based on AHB protocol. I-bus, D-bus, S-bus, and PPB, that is private peripheral bus. Private peripheral bus is used to talk to the private peripheral bus region registers. So the D-bus and I-bus are used to communicate with the core memory to fetch instruction and data simultaneously. And the S-bus interface is used to communicate with the SRAM and to the on-chip peripherals of the microcontrollers. With that note, I would like to end this lecture, and I will see you in the next lecture. Hey, welcome back. In this lecture, we are going to understand about bit banding. What exactly is bit banding? Bit banding is the capability to address a single bit of a memory address. This is quite an interesting feature. This feature is optional, that is, the MCU manufacturer may support it or may not support this feature. You have to refer to the reference manual of the microcontroller. Let's understand what exactly is this concept, bit banding. Let's understand what exactly is this bit banding. Let's say you have memory of 1 kilobyte. How this memory is organized? The width of the memory array is 1 byte. That means 1 into 1024 different locations. That would be 1 kilobyte, isn't it? This is the first location. This is the second location. Let's give one address for that location. This be the address of this location. This is the address of the next byte, like that. If the processor wants to read 1 byte, then what processor would be doing? Let's say read from address 0 cross 2000000. The processor would be reading 1 byte. 1 byte will be returned to the processor. That's what we call as byte addressing. The instruction could be, if you are using ARM Cortex-MX processor, then we have an instruction called LDRB, load a byte. Let's say LDRB R0 R1. R1 is initialized with this address. If you execute this instruction, then 1 byte will be read and it will be loaded into R0. What if you want to read 2 bytes simultaneously? LDRB is byte addressable. This is a byte access. What if you want to read 2 bytes at a time? Then you'd be using the instruction LDRH, where H stands for half word. This is half word addressing. That means 2 bytes will be read and it will be stored into the internal register of the processor. And after that, we have instruction LDR. This is word accessing. We have byte accessing, half word accessing, and word accessing. For this, we use the instruction LDRB. For this, we use LDRH. And for this, we use LDR. What if you want to read only, let's say this is the 0th bit, and let's say this is the 7th bit of the data. What if you want to read just 4 bits? That's not possible. That is half byte access. Half byte access is not supported, at least in this processor. If you want to read half byte, so first you have to read full byte using LDRB, let's say, and then you mask out the bits which are not required. That means the lowest possible addressable size is byte. The bit banding is a feature by using which you can address a single bit of the memory location. This memory location has 8 bits, isn't it? By using bit banding technique, you can address individual bits by using a unique address. That's what we call as a bit addressable feature or bit banding. That means a unique address will be given to each single bit of the memory location. Let's understand why it is required or what is the advantage of this feature. Let's say you have a memory location here of 1 byte, and let's say you want to change the 0th bit. This is a 0th bit, and let's say you want to make this bit position as 1. You'd be doing LDRB. You'd be first reading a byte, let's say to R0 from R1. Let's say R1 is initialized with this address. This is a byte access. After that, you'd be modifying the 0th bit. You'd be using one instruction, let's say ORR instruction or something like that, to modify. This is modify the 0th bit. And after that, you'd be executing store B, strb R0 R1. This is load, modify, and store. Even if you just want to touch a single bit of the memory location, you have to first use byte access, modify it, and then again byte access to store it back. That's a normal method. But if you use bitband method, so this is a normal method. Bitband method is you just use